Ever wondered how a grid of simple cells can evolve into patterns so complex, they seem almost alive? Imagine a row of tiny switches, each either on or off, that follow just a few rules. Over time, these rules can generate behaviors that range from perfectly uniform to wildly chaotic. This is the realm of elementary cellular automata, or ECAs, and today we're diving into how mathematicians are using cutting-edge tools to decode their hidden logic. At the core of this mystery is a fundamental question: how do basic rules give rise to such unpredictable complexity? In the 1980s, Stephen Wolfram classified ECAs into 4 distinct classes. Class 1 rules collapse into uniform states, like a screen filled with a single color. Class 2 rules create simple, repeating patterns, akin to a steady heartbeat. Class 3 rules produce chaotic, random noise, unpredictable and ever-changing. In Class 4, these are the outliers. Their rules generate complex, structured patterns that can even mimic computation. But how do we quantify these differences? That's where this research shines. Instead of just observing patterns, scientists are now counting trajectories, the paths systems take as they evolve toward stable attractors. Think of it as mapping how many initial configurations lead to a specific outcome. But here's the breakthrough. They're leveraging a technique from physics called the transfer matrix method, TMM. This mathematical tool acts like a supercharged calculator, efficiently mapping all possible paths a system can take without having to list them all individually. Here's the magic. The TMM allows researchers to calculate, for any ECA rule, exactly how many starting setups will converge to a specific attractor after a given number of steps. It's like determining how many different routes lead to a single destination in a vast, infinite network. When applied to ECAs, the results were revelatory. Class 1 rules rapidly reach maximum entropy, a measure of disorder, settling into uniformity. Class 3 rules hit a chaotic plateau, their entropy fluctuating wildly. But Class 4 rules, they're the rebels, maintaining a delicate balance between order and chaos. This discovery directly linked entropy to Wolfram's classifications, giving us a numerical framework to quantify what we once only observed visually. But there's a catch. The TMM's power comes at a cost. As the number of steps increases, the computational complexity grows exponentially. While it's ideal for analyzing short-term behavior, long-term predictions become computationally infeasible, even for supercomputers. So what does this mean? ECAs aren't just abstract puzzles. They're a window into how simplicity can birth complexity. Whether you're a scientist, a programmer, or just curious about the universe's hidden rules, this research shows that even the tiniest algorithms can unlock vast, unpredictable worlds. Want to explore further? Check the description for the code and dive into the math yourself. If you enjoyed this deep dive, hit subscribe, because the universe is full of secrets waiting to be calculated. Next time you see a pattern in nature or a simulation, remember, behind the simplicity lies a universe of complexity. Thanks for watching, stay curious.